Good morning. We started chapter 2, so this practice question was from section 1. You can see the name is average rate of change for this function. The average rate of change basically is slope of the graph of the function. So just try to remember how do we calculate slope. Slope calculation. In college algebra, we learned the calculation slope is m equal to y2 minus y1 divided by x2 minus x1. That is how you calculate slope between x1, y1, first point, and then x2, y2. That's the second point. That's how we calculate slope. However, we're talking about slope with a curve, so we don't have y1 or y2, but we have two x values. So that's going to be our x1, x2. x1 is 2, x2 is 4. So how do we calculate slope? You're going to first calculate the y value for f of 2 and f of 4. So you're going to have two y value calculation. Once you have that, you can then follow the slope calculation. This is a couple practice that we did in section 1. We calculated from 2 to 3. So we calculated f of 2, f of 3, and we did f of 2 minus f of 3, f of 3 minus f of 2 divided by 3 minus 2. That was the first example in section 1. So it can be considered as another review of the idea of average rate of change. If we cover up the term average, and that if we only talk about rate of change for any function is a derivative. But if we attach the name average to the word rate of change, average rate of change is not the derivative, it's the slope. So there's a deviation, there's a difference between average rate of change and instantaneous rate of change. Derivative is a very specific way to study a function as far as how fast a function is changing. So it allows us to figure out the rate of change. Therefore, we know it's increasing or decreasing. So derivative bring a lot of information about what would be the function, what was the behavior of the function. All right, so let's first start calculating this example. So let's first identify the y value since we want to calculate the slope. For a function, the y value will be calculated based on the function definition. Right now, f of x is x squared plus x squared minus x plus 4. That is the formula for how do we calculate the y value. So for example, right now we were given the x value 2 and 4. So the first thing you should do is calculate f of 2 and f of 4. The f of 2 is equal to 2 squared minus 2 plus 4. And that will be how you can enter. It's the x squared, so now you have 2 squared minus 2 plus 4. 2 squared actually equal to 4, so we square. You could do the square calculation first, so it's going to be 4. Order operation, exponential calculation is the 2 squared. So 4 minus 2 plus 4. That's the calculation, and you can see 4 minus 2 is 2, 2 plus 4 is 6. To follow the order of operation, we calculate f of 2. We do the same for f of 4, which will be calculated as 4 replacing the x. F of x allows us to calculate the y value for any x. So f of 4 allows you to calculate the y value for when x equal to 4. So you plug in 4, 4. The calculation will be 4 squared and then minus 4 and plus 4. So we follow the definition to find out the y value. And 4 squared 16, so that is actually 16 minus 4 plus 4, which then you can see that minus 4 cancel the plus 4, so the answer is 16. So that allows you to calculate the two separate y value. Once we find the y value, we can start calculating the rate of change. So where rate of change actually average rate of change. Okay, that is essentially the slope. So we are calculating slope from the 2 points. All right, so in order to calculate slope, slope is equal to, and then we mentioned the definition, y2 minus y1 divided by x2 minus x1. Oh. Okay, so that's the definition in college algebra about how do we calculate slope. So right now, the average rate of change or slope will be calculated as so the average rate change is equal to slope, and slope is equal to, you can see we're gonna do subtraction in the y value and subtraction in the x value. Subtraction in the x value is 16 minus 6. We take the two y values that we calculated and subtract them. In the denominator, we'll subtract the 4 minus 2. So that's the subtraction of the x value, and that's the entire calculation. Any question? I hope this specifically gave us an idea on how do we handle rate of change. And this is often something useful later on because the terminology we call average rate of change is also the slope. It's also the average of velocity if you're talking about motion. So let's go back to that page. Okay, let's see. Once your name is lighting up and you know that your answer is recorded, so far everybody's answer is correct. Anyone else? I have 9 answers recorded. That's the calculation for the average rate of change. That's the term average rate of change is actually slope from one point to another point. So now for those 2 points, you have to identify x value and the y value. Slope is calculated by that division. I'm going to check, make sure everyone in the classroom has submitted. So, did you already submit? Cool. Now the answer is 5, as you know from if we finish up the calculation, it's actually 10 divided by 2, which is why the answer is 5. Okay, so that will be today's attendance question. Do you have any homework question that you want to mention? Question about the homework? Did you finish 1.4? Down to 1.4. What about 1.5? Okay, and 1.6. Try to finish the assignment before our test, and then let me announce one more time. The test one is, I should send out email to everyone so we know test time. Exact schedule. It's single display. All right, I believe I remember it's February 7. February 6th. So February 6th is a Thursday. We are here Wednesday on the 29th, and we actually went a little bit faster than the original plan or than last semester when I was teaching this course. So that's February 6th. Let me make sure that I send out email as a new announcement that we even people who are skipping classes would know that it's coming up. Just because sometimes I felt like everybody already know the test is coming up, but in fact they don't. So whatever works to get the schedule posted to everyone. This is a test over, this test is over chapter 1. Wait, repeat all your homework. Yes, that should be it. Sorry, I should really do this. What time? Right, that should give everybody a message. All right, another thing about test preparation, I posted a test folder. All right, on Georgia View, if you open up content to the left, you can see test preparation. So I posted a couple of practice questions for us to kind of see how the test is being organized, what kind of question will be on it. So if you look at it, the first two file, this is an example for what kind of question will be on test 1. Basically, we're hoping to pass over, for example, limit calculation that can be calculated using just plugging the number. Limit calculation that you have to factor the numerator denominator. Limit calculation that may be able to determine using the graphs. Limit calculation, I probably won't put the epsilon delta definition because that tend to be lengthy. Algebraic method for finding the limit calculation involve roots. One-sided limit. So you can pretty much open this file to see the format of how it's being organized. And these are a couple questions that we might have done before. So this one is the interval notation. That's calculating a limit that kind of related to the derivative. This is the one-sided limit using the piecewise diagonal function. That was the one question about motion. I could change the set. Maybe I should remove this. Okay, I did put the solution up. The whole solution is using limit as a calculation tool. So anyway, I think I covered the screen. All right, so these are multiple choice questions as far as the limit calculation, which has a limit involving infinity. We also have graph where we determine which function has a limit, which graph has no limit, or which function of the graph that has no limits. So that was a example on graphic interpretation of limit, and there's one bonus question. So that's pretty much the structure of the test. It won't be exactly that way. That was just for example. So this is not the real test, but it will be very similar to the real test. So hopefully this give us some comfort that you already know how the test will be structured. So that also is something that you can use to practice for the test. Any question? All right. If there's no more question, we'll continue where we left yesterday. I realize the first section on chapter 2 is long since we used 2 days already. 2.1, but it's better for us to go through the concept of derivatives slowly rather than fast. So the idea of using slope calculation and determining the limit of the slope is where the derivative coming from. And that's why we see more and more of that division and of that slope calculation. And review. 2.1 is our introduction to the notion of derivative. We interpret or define the derivative as instantaneous rate of change. So in order to introduce the idea of instantaneous rate of change, we started by the average rate of change. So what we did is taking out time interval. The first, we got this function about motion, something moving. So the height is being represented by ft. So this is a function describing motion. The first interval is 2 to 3. So we're going to take 3 minus 2 after 3 minus f2. We got negative 80. The second interval, we have 2 to 2.5. And this is already on your notes probably. And we talked about this yesterday and the day before yesterday. Right, and then the third one, we have an even smaller interval, 2 to 2.1, and then 2 to 2.01. As you can see, the length of the interval gets smaller and smaller. The first one, we have the interval have a distance of 1. The second interval have this 0.5. And then this one is interval from 2 to 2.1. The weight of the interval, the length of the interval is 0.1. And then you can see 2 to 2.01, the end value minus the beginning value is 0.01. That's literally the h. H represents how long it is from the initial x value to the terminal x value. That's the h. All right, as you can see from our example, we're illustrating the fact that as these 2 points get closer and closer together, the slope is approaching a certain value, and you can see the change is getting smaller and smaller. At first, between 1 to 0.5, we change from negative 80 to negative 72. That's a big change. However, then we change from the negative 72 to negative 65, smaller change, and then 65 to 64.16. That's even smaller. So as the h getting smaller and smaller, the change, it has big change and small change, and then when h gets even smaller, these two are also approaching a certain limit value, and we realize that facts, and we take a endpoint, a arbitrary endpoint, and instead of a definite endpoint. So instead of 2 to 2.01, we have 2 to 2 plus h. So the h will be the 0.1. And then we're going to try to calculate what's this slope? What is this rate of change? So all these calculations are average rate of change. And then over here, using limit of h approaching 0, we're calculating instantaneous rate of change. This is a ratio between the change in height over change in time. And then when we're taking that limit, we are determining the instantaneous rate of change. So going through the algebra, finding what is f2, which is really the negative 86, and finding out f2 plus h, which then will be a formula. Finishing up the substitution, we end up having a expression that has no number term. We don't have the degree 0 term, that's degree 1, degree 2, and then degree 1. And then dividing the h, we have an equation. When h is approaching 0, we have negative 64 as the instantaneous rate of change. So that's the first introduction of using a limit value to define the derivative. That's just really the derivative of the function at point 2. So 2 is a point of tangency. 2 is a derivative point. And negative 64 is the actual slope. That's the derivative value. That's the slope of the tangent line. So that's the official definition. I hope by now, when we look at it, we kind of know how it's being structured. It's basically a derivative limit of a slope. Numerator is subtraction of the 2y value. Denominator is a subtraction of the x value. X value is c plus h minus c. So that's subtracting those. That's how you get h. So this is really a slope calculation, or you can call that the difference quotient. Difference means it's subtraction, quotient means the division. So this is the difference quotient. Limit of the difference quotient give the derivative. So you can try to think of a way to make sense of this formula. The next time when you have to define the derivative using the limit, you know how to do it. So the key point is we have to be really, really familiar with it to be able to apply it. So if it's new to you every single time you solve a derivative question, that will be an issue. So I would recommend to, if you are unfamiliar with something, write it down and then apply it. Write it down and then apply it. As you solve more and more questions, you start realizing that you don't have You don't even have to write it anymore because you already know it in here. So frequent application often calls us being able to apply it faster and remember it faster. So that's the definition for differentiability and differentiable on the interval. Okay, when we also have this definition that we know that the derivative is actually slope of the tangent line. So because we know the slope, we're able to define the equation of the tangent line. So knowing the derivative and knowing how to find the equation of tangent line become like one of those exercises in section 1 on chapter 2. And we have a couple practice. I did the point 1 actually, and that one has a solution in the book. So it's a very similar procedure, similar steps when we try to work out these two pair of problems. So we did this question for exercise, and then we also have the definition for the normal line. Normal line is going to the same point. One is a tangent, one is a perpendicular to the tangent. So those are two lines that intersecting each other at 90 degrees, and their intersection point is a point of tangency. The point of tangency is a point C, F of C. The C is the X value, F of C is the Y value. This is really a point slope formula. The point is there, it's in the equation. The slope is also indicated by the formula. And of course, this is a hypothetical equation for the normal line, but when you actually calculate it, all of them supposed to be numbered. That's the number for the slope, that's the number for the point. C is the X value, F C is the Y value. All right, any questions so far? I mean, we've done this before. I was just trying to make sure that we kind of everything come together as a whole rather than only continue around where we left. We practice calculating the normal line, determining the normal line from that example. Yeah, this is where we ended. If you have a function that is a linear function, then the derivative equal to a single number. So to be sure that f prime of x in this case, so if you have f of x is equal to 3x plus 5, then you know the derivative that says f prime of x, the derivative equals 3. Okay. Derivative of a function is it's the slope of the function. So if you got a function that's 3x plus 5, you know immediately that that's mx plus b. So the slope is 3. So derivative has a lot of connection with slope, and slope has a lot of connection with direction. So when you think something have a slope of a certain value, you're saying the function is going in that direction. If we think about equation of the line, there are the two components for an equation of line. First, you have to know the position, like where is the location of the line. 2, you have to know the direction of the line. In this case, the 5 is determining it at 5 on the y-axis. And then the 3 is saying that we're not going this way, we're going this way. So if you want to graph it, function, right? The 5 is tell you the location right here. You have a 5 on the y-axis. Y equal to 5 is what happened when x equal to 0. So that one controls the location and the high or low. For example, if you have 3x minus 5 for your function, it will look like this. It's the minus 5. All right, and then the 3x is the direction. So this is saying that 3 is going positive, go up. So that's 3x plus 5. But this one is 3x minus 5. So I'm going to go same direction, but it's at lower position. I'm trying to illustrate that both of them control the different component of the function. 3, the slope, control the direction. Any question? Okay, so any function that has the same slope, they're parallel. I draw them onto a separate graph. You can actually draw them in the same graph. One is higher, one is lower. All right, a little review on the linear function. Okay, so now this is the definition for the derivative of the function. If you compare this with what we have earlier we have f prime of c. Now we have f prime of x. So what's the difference between f prime of c and f prime of x? I think there's really no specific difference. The only difference is X is a common letter that we're using for independent variable. C is normally what we're using for a specific value. So normally C is not considered a variable. So you're saying C is the point of tangency. The reason we use C earlier, because you already have f of x. Now, if you have f prime of x also, it coincide each other and people would be having a hard time differentiating them. So why are we calling them x here? Why do we switch to x? Because derivative is also a function. So when you are determining this function of prime of x, you are thinking, give me an x value, I have an f prime of x. If give me another x value, I have another f prime of c or f prime of x. So when you're changing this input value, you are changing your point of tangency. Therefore, you got a different tangent line, different slope. So that is also corresponding between input and output. So that's why we can consider derivative as a function instead of consider it as a single value. And we observed that from before, f prime of c will take on different value for different function. Also, if you change the number c, you get different value for f prime c. That's why it's actually a function definition. There we have it. All right, so in our text or homework, if you are required to calculate, let's say this is how a function is defined, let's find f prime of x. This is what you want to use to calculate the function. So what is the reason for this is c that we had before normally is a number, but x here, it could stay as x. So that will be a function. This will also be a function. So very likely for this kind of computation, you work with function and you are trying to find limit value of a function. So this limit calculation might be harder because we're not finding a number for the limit. So you cannot plug in number to solve your limit value. And that leaves us only one option. So determining the f prime of x, you often have to find the analytical way of solving this limit because the answer to this limit calculation is not a number. It's a function, which would have to have the x maintained in there. The limit when at h approaching 0, meaning h is pushed onto a 0 value. So your final answer do not have h because h already gone or approached 0. But your final answer to the entire definition of f prime of x would have x in there because this f prime of x is a function of x. It's a formula of x in there. All right, so that is the definition. We're going to start looking at a couple of examples for that when we were moving on. All right, the bottom half of this page is a couple of notation. As you can see, f prime of x is our first definition for the derivative function, right? And then we have a couple of other notation. Why we have so many notation for the derivative? Well, it's because of the history of calculus. It was derived across the coast from a very different set of mathematicians. They come up with a notion of the idea of derivative and calculus, fundamental idea of calculus. When they are working with a completely different group of people, they both thought they would be the first one that invented calculus or come up with the ideas in calculus. And actually, if you look at the history of calculus, there's something called the calculus war. That way, the leader of one set of mathematicians is Newton. Newton and a bunch of his friends, they had these function notation f prime of x, and then across the coast in Europe, Leibniz is the one that come up with a different set of calculus notation. That's the dy dx. They were using the differential notation. So here are the function notation for the derivative, and those are the, let me try to write it. So these are what I consider the function notation for the derivative, and then over here is the differential notation. The differential notation for the derivative, they're actually the same thing. That's why they're all equal. Okay. So about the one on this side is you can see the reason that we call it f prime. The prime is adding a little something to the notation of f of x. So f of x f is a function name, x is the input. So that's really function notation, which is why a lot of time we have the habit of writing f of x instead of h of x, instead of q of x. Why don't we use the other letter? Because f is the initial letter of the word function, and people call it a function because when one input is putting in, you have an output. Function is the relation between input and output. When every input has only one output, that is a function. All right, so really y equal to f of x is relation between input and output. So adding a little prime to it, we're indicating that the derivative is derived from that function. So f prime of x is a byproduct, or is something that calculated out of fx. Those are the calculation. It's a complicated way to calculate and define something out of a single function, but still it completely based on f of x, you have f prime of x. So that's the first notation. And then why do we have y prime? We have a y prime because this notation, you see y is equal to f of x. So if you have f prime for your derivative, you could also just simply do y prime for f prime of x. So that's this y equal to f of x, consequential essentially gave you f prime of x equal to y prime. And they're essentially the same thing, and then they're rooted in the function notation or the idea of how function works. All right, on the other side, okay, what will be the difference? What's the reason for this? It's based on the definitions. You see over here, we have the subtraction of fx plus h minus f of x. That's changing the y value. We often use a little triangle notation. This is a change in y, all right? We're dividing the change in y by the change in x. Okay, so x plus h minus x is changing x. So this is a difference quotient. Change are the difference, and we're dividing the difference. That's why it's called difference quotient. So basically, the derivative is the limit of the difference quotient when the delta x is approaching 0. We spell that triangle is a capital letter in the Greek alphabet pronounced delta. Okay, that's why I keep saying delta x and delta y. Those are representing the changing y, changing x. All right, and then we will be like, if you want to represent the entire thing, Leibniz has a notation that we want to represent that division relation in the division. Instead, we call that dy and dx. The reason that we talk about dy dx because d is an initial letter for derivative or derive. So it makes sense calling them d this and d that. So, and also we have a name for each of individual of them. This is called, this is derivative, and we see function is differentiable. We call this the differential of y. Okay, I think I kind of finished. All right, so that's differential of y, and then the denominator dx is actually differential of x. So you can see we have the differential for each individual variable. So those are what I call a differential notation for the derivative. And then many of them are rooted in the fundamental notation as well. Now you can call it dy dx, but what is y? Y equal to f of x. So you can also call it the f dx, the f dx, and then also because the derivative computation is not a multiplication. So when you write dy, we're not multiplying d with y. We are using dy as a whole notation. Dy has meaning, but d, what about d itself? Do we have d onto the x? We multiply d with x? No, dx is the h. Dx is a delta, it's changing x. So there's no special thing about it. So dx will always be together. But it's not the same thing for the dy or dx. You can see sometimes they're being separated. Okay, dx will always be together. But in the numerator, sometimes they are being separated. Why are we separating them? Because we feel like determining the derivative is a process onto any function. So let's say you got this function f. All right, and we can try to find the derivative. So from the f to the derivative f is a process of determining this is the derivative, and this is the calculation. That process we call the ddx process. Right, so we also say df dx is the same thing as dy dx because y equal to f. So y equal to f, therefore dy dx equal to df dx. However, you can separate them instead of thinking of the whole thing as a whole notation. We consider this as a process. You got a function, let's find the derivative. So ddx is a notation for finding derivative of something. And for example, we mentioned before, if you got a linear function like c ddx of 3x plus 5, 3x plus 5. So this will be a process of that. Let's try to find the derivative of 3x plus 5. So the answer for this calculation will be 3. Okay, so then, which basically says the derivative of 3x plus 5 is 3. So this kind of notation allows us to put the original function and the derivative function in the same equation. On the left, you have the original function, that's 3x plus 5. On the right, you have 3, which is the derivative function. And that doesn't come easy because in the original function notation, you have to write f of x equal to 3x plus 5. So f prime of x equal to 3. So you have to write 2 lines of equation in order to express, hey, this is the original function, this is the derivative function. So now the ddx notation allows us to put, we're trying to find derivative of this function, and that we end up getting by 3. So this representation have a single line representation pairing the original function and the derivative function in the same notion. That's the other two notations. So ddx of f is trying to find the derivative function of function f. Now ddx of y is trying to find derivative function of the formula y, whatever the y is. In our case, the y would be 3x plus 5. I hope that kind of makes sense of the notation. Are we okay? So you don't have to be immediately know what's going on. And either have this notation have their historical reason. Most of the time we use f prime of x, but in the future, occasionally the dy dx will pop up because differential itself, the dy dx or dt or du, d whatever variable, eventually will be part of the calculation for integral. So in the second part of the calculus, we have to talk about how to integrate a function. Integration is the opposite of differentiation, so that kind of brings out necessity for us to be familiar with both notation. Right, so right now we can stay with the different the function notation, and in the future we'll gradually add more practice on the differential notation. Any question? The rest of the section, I believe, is more practice on applying these notation and determining the process. Okay, so now this one. So the question says, we have this function, let's find the derivative function. This is called the original function. No, this is called the derivative function. They're corresponding to each other. Like I said, derivative function is derived from the original function using the limit definition. So we're going to do it according to the definition we just introduced. So let me copy this and we're going to start working on calculation. Right, so first is know what we're trying to do. We already know the f of x. Our goal is to find f prime of x. So you know what you're trying to find, and now you have to try to figure out what would be the connection or what would be the formula for f prime of x. So right now, since we just introduced f prime of x as a definition, I'm going to write it down. F prime of x is equal to, hope that you have it, write it down on your notes, equal to the limit of the numerator will be f of x plus h. And you can see it's an abstract notation. Occasionally I have students that give up on the limit definition of derivative. They feel like it's too complex. Also because later on we're learning a lot more other ways to determine the derivative. And then we tend to take the easy way out instead of the limit notation. But if you're into pure math, limit computation or understanding limit will be a key issue, and people have to write paper based on the limit definition of a lot of things. So, if we have to compare, we should really compare early or try to approach the idea, the method early as early as we can. Right, so we're gonna try to write it out. This right now is what's in the definition. You can see it's very close to what we just did in section. Well, this is section 1 at the beginning of section 1. All right, so we're gonna write it out. You can see here we need two things in the numerator. There's really no problem about the denominator. That just be a single term of h. Numerator is where all the action comes from. All right, it's a subtraction, and here we have f of x minus f of x. And what's f of x? This is f of x. So you can see the process is different than when you have a number. If you have a number, let's say f prime of 1, and you're going to go ahead and calculate f of 1 and calculate f of 1 plus h. Now we have f of x. That means none of these two are numbered. They're both functions. So the first one is plugging x plus h into the function, so the x is replaced by x plus h. So that it looks like this. So numerator will be 3 times x plus h squared plus 5 x plus h minus 7. And then minus f of x, and the f of x is out of space. All right, f of x is the original definition, obviously. That's the f of x. Just move it all over here. That's f of x. Okay, so that's the actual calculation of it. So the first thing you have to notice is that numerator require two things, and these two things are very similar. One is f of x, one is f of x plus h. So in the f of x plus h, the x is replaced by x plus h. So it's a bit more complex. Really remember to put in the parentheses so the order of operation will be included. And now this step is from the definition to the actual function. We are rewriting the entire limit calculation by noticing the true meaning of f. Where f is supposed to be, it's that f of x is a formula, so that's f of x formula, and it's f of x plus h formula. So now we have actual calculation. All right, and as you remember, since we did a couple examples already, when you're doing this kind of calculation, when h approaching 0, we have division by 0. But more to that, it is actually 0 divided by 0, so we know that all these terms, they should be canceled. Now you should have a single term in the numerator that have h as a common factor. We should be able to cancel the h for that matter. So all these terms, the 3x squared, 5x minus 7, they should be canceled. And we see them canceling each other already. Right, try to mark it out. That's minus 7, but it's minus negative 7. And here we have a true minus 7. So minus 7 minus a minus 7, they cancel. So the 7 is gone. And then over here, we have a 5x minus 5x. Now there's a 5x there. So the 5x will be 5x minus 5x. They get canceled. Another thing is there are terms here. You can see that 3x squared. So 3x squared, we have 3x squared there. So we know for sure that those terms will be able to subtract out or will be canceled. So the answer to the simplification of the numerator will be look like this. It's limit of h approaching 0. Okay, I have to expand this. 3 times x squared plus, that's x plus h times x plus h. If you try to calculate it, right, that's x plus h squared, and then you have x times x, h times h times x, and h times x. So altogether, it's h times x twice, so 2h times x, and then there's h squared. Right, so that's expanding it, and then the 5x, and then 5h, 5 times h, and then minus 7. right? Everything else unwrapped, there's minus x squared, there's minus 5x, and there's plus 7. Mine looks long. I hope that you have space on your notes if you're following this process. All right. I'm just trying to analyze this, say something can be canceled, but before I cancel them, I'll expand this. You can see how they were being canceled. The term that canceled are the plus 7 cancel the minus 7, the minus 5x cancel the plus 5x, the negative 3x squared cancel the positive 3x squared. So what do we have left after the cancellation? We have this is equal to limit of 3x squared is gone, so we have 3 times the 2hx, so we have 6hx. All right, and then we have 3h squared as I distributed the 3, but I know the 3x is gone, so that's the 2. 3 times 2hx, 3 times h squared, and then we have the 5x, cancel that 5x, so we still have the 5h, so plus 5h. And there's no more. So the 7 cancels 7. Those are all cancelable. All the one that I marked out is gone, and that's the only 3 terms that we have left. If you try to count the terms, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 terms, and 3 cancel 3, so 6 is gone. That's why we have only 3 terms left. So number of terms seem to agree with our analysis. So we divided by h, and then h is approaching 0. So this is limit of calculation when h is approaching 0. Now this calculation shouldn't be too hard. We have a division of a single term, so you can divide every single one by the h. So 6hx divided by h cancel the h. The first term after the division is 6x. And then the middle term is 3h squared divided by h. 3h squared divided by h, you cancel one of the h, so that is 3h. And then last one, we have 5h. The 5h will cancel this h. The h get canceled, we have a 5, so plus 5. And then we're gonna let h approaching 0 if h approach 0. But the 3h is 3 times 0 because h approaching 0. So 3h is 0. So after h approaching 0, we have no more h because h equal to 0 now. So then the answer is 6x plus 5. And that's the derivative. Okay, so we're going to try to answer the question here. The answer to the question, try to block it out. The one we just calculated, we realize that f prime of x is equal to equal to 6x plus 5. That will be the answer. So if f of x equal to 3x squared plus 5x and minus 7, you see what happened in the derivative. And same to have 3 separate terms. So for at least the 5x minus 7, remember it's a linear term. When you have a linear term, the slope is a number. So for 5x minus 7, the slope is 5. Derivative of 5x minus 7, the derivative is 5. Now we know from the past. Then we have 3x squared. The derivative of 3x squared is 6x. If that's kind of like having the 3 times 2, and then the x power goes down by 1. Instead of degree 2, now we have degree 1. It's the derivative. So we can gradually say some example and try to make out the rules or underlying pattern from the relation between the derivative and the original function. Any question? Sure. So this is our first example using the limit definition to determine the derivative from the beginning to the end. This time I didn't separate them. Some students like to separate them. You can calculate f of x and then calculate f of x plus h and compare them. So when you subtract, you can compare them one by one. Then you can do the subtraction. So if you want to single out all these by itself and then finish the simplification, that also works. This time, because they're abstract, so I didn't really separate them. So I started with the limit and continue with the limit computation and finish the limit calculation. So this time I didn't pull things out. If it's number, I will probably pull them out and try to simplify them so they can be concise. And these are all abstract letters and variables, so I kept them in the limit computation. So this is a first example. And I'm gonna see a couple more example on determining the function of the derivative. All right, so this is our second example. How do we find derivative function? So we're not trying to find the derivative value anymore. And if you compare this with what we did before, like way before over here, what we did, we derivative the value at prime 1, we did, that was 11. Over here, this is f prime of 2. You can see that was 2. So we have f prime 2 equal to negative 6. So back then, we have a specific number, like that's number 2. But now we're trying to determine the derivative formula. So then the answer to this limit calculation is a formula because we're not making x equal to anything. We're leaving x in there. That's why our answer also have x in there. So try this example. Suppose you have a division, a fraction as your function. What is a derivative? It will involve a little bit more algebraic maneuver. Let's see if we can follow. Okay, so first thing is try to write down the definition so we can follow. Start from there. So we have f prime of x is equal to limit of numerator will be f of x plus h minus f of x. This is divided by h, and h is approaching 0. So make sure you write it down. And then you're going to compare what you have. In this limit computation, you need f of x, you need f of x plus h. They're very similar. So understandable, their representation is also similar, but let's try not to make too much mistakes in the process. Okay, long-term h. This is a subtraction. The f of x, there's no change. This is our f of x. So f of x is 1 over x plus 1. Okay, but the first term is f of x plus h. So it's also going to be 1 over, and you're going to do a substitution. Whenever you have the x, now you have to write x plus h. So it would not be, it would be the right way to, it will be 1 over, that x itself become x plus h. And you still have that plus 1 in the denominator. So that's how it looks like. Occasionally I have students, they write it wrong. They write like 1 over x plus 1, and they get plus h there, and then they minus 1 over x plus 1. And you can see what happened. That's going to be a h. You're going to get h over h. They think like the derivative equal to 1, but it's not. So we try to be careful and make sure we didn't change the function format along the way. So we try to change the maintain the function format, but do the substitution the right way. Okay, so that's how the limit calculation is now. So we have a slight issue here because the denominator in the numerator, there are fraction. In those fractions, subtraction fraction, we have the denominator. The denominator is not the same. Okay, only when you try to subtract fraction, only when they have the same denominator, we will be able to subtract. Now, how do we do subtraction if the denominator is not the same? How do we do it? Do you remember? Yes. No? How do we subtract fraction that has different denominator? So for example, what if we want to divide, subtract 1 over 3, subtract 1 over 5? Do you remember how do we do the subtraction? Anyone know how to do the subtraction?
Denominator.
Which is
15.
15. So we will do common denominator. We will do We want both of these fractions have the same denominator, so we go 15 here and then 15 there. Common denominator will be 15. This one, if 3 become 15, you times 5. So the numerator also times 5, you get a 5 in there, right? That's, you're going to change one fraction to another fraction. They're the same thing. So 1 over 3 and 5 over 15, the same fraction, same number, except now it has a different format. The reason that we change the format because only when the fraction have the same denominator, here we go, subtract. So we do the same. The other fraction, we change from 5 to 15. That from 5 to 15, we times 3. Therefore, this numerator also have to times 3. 1 times 3, which then give us a 3. So the answer to the entire calculation will be 15 is the denominator. The numerator is where we subtract 5 minus 3. So then the answer is 2 over 15. You can use your calculator to double check. 1 over 3 minus 1 over 5 is 2 over 15. So that's how we handle subtraction fraction that has a different denominator. Yes. Okay, so we have to do the same. We want to find the common denominator between these two fractions. Now, do you know how do we know the common denominator is 15? How do we get 15 from 3 and 5? We multiply them. So the denominator can be expanded to a bigger denominator in the hope that they will have a common denominator. So we would do the same in that numerator. So this is what we're going to do. We are going to change the denominator instead of we still have that over h. This is going to be x plus h plus 1. And then time, my writing is bad, time x plus 1. Okay, that's the first fraction. Second fraction, we do the same. It will be x plus h plus 1, and then time x plus 1. So that's how do we want to change both of the denominator. We want to change both the denominator to a common denominator where it contains all the stuff that we want to contain. Okay, so you can see the original denominator in the first fraction is x plus h plus 1, which we already have x plus h plus 1, but then now we wanted to contain a little bit something more. We have an extra x plus 1. In order to make sure this fraction equal to this fraction, those extra things in the denominator has to be extra things in the numerator, because that way it will equal to the original fraction. So that's going to be x plus 1. So that one, you see this, you can go backward. You can cancel the x plus 1. Now it's back to there. But we're doing the reverse. We're not simplifying it. We're artificially trying to make it more complex fraction. We're multiplying things because after you make it more complex, we now have the same denominator. And now we can do subtraction. All right, the same thing for the second fraction. In the second fraction, we already have x plus 1. So we don't have to do anything to the x plus 1, but we have something extra. We have the x plus h plus 1. That is extra, and that extra things have to show up in the numerator to balance the fact that we do not have that extra things. Whatever you have extra, you make sure they also show up in the numerator, because that way it will equal to the original fraction. So the original fraction was 1 over x plus 1. Now you have this new fraction in the same place, replacing it. This is replacing this because this equal to this. You see, if you cancel this common term, it would just be 1 over x plus 1, which equal to that one. So make sure whatever you're replacing the last fraction is equal to each other. So that means this limit calculation is still equal to this limit calculation. We did no change, but we made it possible that they are having the same denominator. Now we can do subtraction. Any question? All right. So with that, we would subtract, and then you can see x plus 1 minus x plus h plus 1. The subtraction, the minus sign in the middle, will affect all the signs in the second term. That's how we do subtraction when we have multiple terms. So this limit calculation is going to be this. This is equal to limit of h is approaching 0. This is division by h. Let me just write 1 over h here. division by h is multiplying the reciprocal, and now we have this, and that will be the x plus h plus 1, and that's x plus 1, right? I'm gonna subtract the numerator. The first term is x plus 1. The second term, let's try to write it specifically, it's gonna be minus x minus h minus 1. Because the minus sign, it's going to affect every single term. So they switch to a negative sign because it's subtraction. Any question? Are we okay? All right, the denominator h, I write it slightly differently because now we have two layers, numerator, denominator. Before, you see how what happened? We have big numerator and the denominator. In the numerator, we have numerator, denominator. So this expression is called a complex fraction because it has fraction inside the fraction, which is why we call it complex fraction. To make it simple, this division of the h, because there's only one term, so it's easy to write it off to the side. Instead of below the whole fraction line, we write it to the side and write 1 over h. So if you have something divided by 2, is multiplying by 1/2. So division of the h is the same thing as multiplying 1 over h on the side of everything else. So this kind of shifted the focus of the calculation to the numerator part of it without forgetting the division of h. So we put it over here. We can handle everything here and then deal with that division of h. I hope it's okay of changing the format. So this helps with the following steps. Otherwise, you keep writing the layers, like stairs of stairs, layer of layer fraction. It makes it harder to see the relation and also made it harder to write it down. So the better way to write fraction normally is the proper fraction, numerator, denominator, numerator, denominator. That's it. Okay, so let's finish this fraction. This x minus that x, the x is gone. This plus 1 and then minus 1. The 1 is gone. So what we have left is negative h. So then the limit calculation becomes this, and this is the equal to limit of h is approaching 0, and here you have 1 over h. Here you have negative h, and in the denominator, we have x plus h plus 1, and then x plus 1. Okay, so if we finish the subtraction in the numerator, we realize the numerator gets so much easier to handle. It looks like the same way that everything that has no h is gone in the numerator. That and that cancel. You have a single h in the numerator, and that h will cancel this h. The h in the numerator cancel the h in the denominator. So now our fraction become this. Try to make it. That's what happened. Right. Try to make it more space. All right, this is equal to, try to fit them all in the same board. H is canceled, you have a negative 1, after's canceled, and the denominator is x plus h plus 1 times x plus 1. And now we have h approaching 0. If h approaching 0, that h is 0. So the final answer to the limit calculation is negative 1 over x plus 1 times x plus 1. Because h is now 0. Now you can make it more concise and write negative 1 over x plus 1 squared. But, all right, so basically, the final answer to the question is the original function is this, and our derivative function is negative 1 over x plus 1 squared. So that gives us the indication that if your original function is a fraction, your derivative is also a fraction with a higher order in the denominator. So here we have a denominator of degree 1, and there we have a denominator of degree 2. And that's, you can consider that as a pattern or a rule for derivative computation. Any question?
Where's the h going? On the
This h
other one.
over there,
Yeah, two.
the h approaching 0.
Oh,
So that's 0. Then x plus 0 plus 1. It's x plus 1. Okay. Any other question? So this is one of the examples how we handle fraction. So I guess this complicated part is from here to here, we have the fraction to the one that has a common denominator. So we hope that hopefully we keep track of the reason why we added that extra thing and why the subtraction correct. And when you finish subtraction, now we're able to cancel common factor, and then the final answer will be a simplified version where substitution actually works. So this is the example. So now we have polynomial and finding the derivative. We have a fraction and then finding the derivative. The next example is. All right, so this is one we want to find the derivative of f of x equal to sine of x. I guess that will be a little bit more complex. It's a trig function. All right, so we're hoping to find derivative of all the common functions. For now, we have polynomial derivative is another polynomial. Division has a derivative. That's another division, the one we just did. And then you can understand if you have a trig function, the derivative will be another trig function. So we're going to try to work out the detail to show which derivative, which trig function is the derivative. Copy that over here. Okay, so we're gonna follow again the definition for the derivative since that's all we have. We haven't learned any easier, shorter method for the computation. So for now, I'm gonna write down the definition and start applying it. Limit of x plus h minus f of x over h, and then h is approaching 0. So this is equal to h approaching 0, and there's no change to the denominator h. But in the numerator, we're going to try to write f of x. We're going to replace the definition. The definition is an abstract notion that applies to all functions, but you have to calculate it to make it useful. So for now, they're just abstract definition of derivative. So I'm going to replace the f of x. That's for sure. We know the f of x is sine x. So that there's no change. So just do minus sine of x. That's the minus f of x. Okay. And then the fx plus h, meaning that in the f of x, you're going to replace that x by x plus h. So instead of sine x, now we have sine x plus h. So look like this, sine x plus h. Okay. So now we're looking at something very, very hard to do because our hope is, and we knew it's what's happening. If h is approaching 0, denominator is 0. What happens to the numerator? If h approaching 0, sine x plus h approaching 0 is sine x plus 0. So that's sine x. So numerator is essentially when h approaching 0, the limit of the numerator is sine x minus sine x, which is also 0. So 0 divided by 0. So we're trying to find a common factor out of the numerator that has h in there. But now it doesn't have any of those. So we have this problem. We won't be able to finish this little calculation without doing some major change to that division, that subtraction of sine and sine. In trigonometry, there is this formula called summation to product formula. And if you remember, if you have sine A minus sine B, whatever angle it is, for this we have a formula. Do you know what was the formula? Anybody remember the formula? This is a subtraction you can consider as a summation of a negative term. So that's summation. So we wanted to write into multiplication because we're hoping for like cross out common factor. We're hoping numerator and denominator have something that we can cancel. So multiplication will be a better format than subtraction. So we're hoping to rewrite the numerator into a multiplication. I think it was like this, it equal to 2 times sine of, it was sine of a plus b, a minus b, over 2 times cosine of a plus b. Over 2. Okay, that's called sum to product formula. Any question? Do you remember sum to product formula in pre-calculus? Product to sum to product. Do you remember? No? The product to sum allows you to write multiplication format into summation format. Now, the sum to product allows you to write summation format into multiplication format. That's what I was doing right now. Let me just give you the whole formula. It actually is a system of formula. It's not just one. It's 8 different formula. I'm trying to write sum to product. And this will be on. Will be. Try to enlarge this. All right. Okay, so you can see if you have summation of sine A equal to 2 times sine A plus B equals sine A minus B. If you have subtraction, which is what we're doing here, we have subtraction of 2 sine. Sine A minus sine B equal to 2 times sine A minus B over 2 cosine A plus B over 2. So kind of switch the angle there. So sine A plus sine B, sine A minus sine B are very similar. And then if you have cosine minus A minus cosine B, cosine A minus cosine B, it's negative sine times sine instead of cosine and times sine. Now it's sine times sine. If you have cosine A plus cosine B, that is 2 cosine A plus B and cosine. So there's cosine for cosine. All right, so these are 4 formula. That's for the sum to product formula. And there are, oh, this is a better representation of it. So those are the formulas. We're using the second one of the whole bunch. There are really 4 formula for the sum to product. So calculating derivative, we often think of multiplication is easier than subtraction because we're hoping to cancel that single h in the denominator. Now, there's also product to sum formula. Are we proving it? There's a proof of this. We will probably gonna see this. Sometime you want to have summation instead of product. So there is this product to sum formula. Where is it? So this is how you write multiplication into a summation. So sometimes you prefer them separate as subtraction or summation. When do we want to do this? When we were trying to do integration, say in Calc 2, you want to integrate the function, and instead of having the multiply format, it's very hard to find the antiderivative. Instead, we want to write it into separate term. You find this function's antiderivative, and you find the other one. We can find them one by one if it's a summation format. So there are situations we prefer having them separate as summation. There are situations we prefer them having them into a multiplication format. So applying this formula, we will have this is equal to limit of h is approaching 0. In the numerator, we rewrite it as 2 times sine. And that was the formula that we mentioned. We're applying this formula. So this subtraction, now we want to have a subtraction of the inside. So x plus h minus x, which is going to be h. I have h right here. So this is h over 2 for this one. Okay, so this is our a. X plus h is an a, right? And then the x here is a b. So for a minus b is x plus h minus x. That's why we have a h. X plus h minus x, cancel the h. That's that part. And then you multiply this by a cosine of, so the cosine part, we were supposed to have, see, that's supposed to be summations. We have the x plus h, this one, add with this one this time, because of subtraction we add, and you have 2x plus h over 2. So that's how it looks like after we've done that. And then we can see h is approaching 0. Okay, now what's this one exactly? What is making it slightly easier to do is that you can see in the numerator we have sine of h over 2. In the denominator you have h over 2, but bring that 2 down to the h there. And over here you have cosine of 2x plus h over 2. Okay. So when h is approaching 0, remember sine x over x. When x approaching 0 is 1. Therefore, sine x and x is very close if x is approaching 0. So basically, if h approaching 0, h over 2, sine h over 2 are pretty much the same ratio. So sine h over 2 and h over 2 are around 0. They're pretty much the same. So this one have a limit value of 1. So then the calculation would be making h approaching 0 over here. You have cosine 2x. So it's going to be cosine 2x over 2. Okay, why is cosine 2x over 2? Because cosine 2x plus h. H is approaching 0, so then you really have 2x over 2. So the derivative of 2x over 2 is really cosine x because the 2 is canceled. So derivative of sine is actually cosine. That's really the mathematical proof of it. In the middle, we did apply a trig formula, and you can confirm this trig formula is true for any angle. So it does have a little bit tricky part in the limited process, but that's because we're dealing with trig function here. And that'll be for today, right? So that's the definition here. Are we okay? Was it too hard?
No, I was tired. As you go better.